Okay, so let's continue. The second speaker is Mohamed Bouyan from Sintef in Norway, and he will talk about the role of osmosis during drilling in shale. So please.
Thank you. Can you hear me? Okay, thank you. Did you guys notice that I am talking about drilling, right? But did you see anywhere drilling on this picture? No, because we become black now, right? Oil and gas is black. It's not green anymore. So the Sintef, even though the oil and gas provide significant amount of money to the society, to the country, but they like to put us behind. We still works, we still exist, but we kicked out of the template. And this is the template we are not forced to, but we are advised to use this template when we present something outside. So first of all, I would like to thank the organizer to give me the opportunity to come here. This is first time for me. Not first time in India, but first time for me in this Fracmeet. But it's not the first time for Sintef to be here. My colleagues, they came, and the colleagues who came before to represent Sintef in Fracmeet is mostly the theoretician guys. So they all discuss or work with theories like Erling Fehr or Rune Holt, all those people. But I'm not. That was a little bit too much for me last 3 days. But anyway, I tried with my open mind and open thing, and I get something that I will take with me and try to implement the experiment. So my background is geology and geophysics, mostly geology, and I worked in the oil industry. I worked as a petroleum geologist, and then I did my PhD in rock physics. So I got a little bit of physics over there. And when I started in Sintef, I started with this topic actually. So I got a bit of a physics and chemistry and then my geology was a little bit there. And I will talk about a little bit Sintef first. If you don't know about Sintef, it's a research organization. So here we are. We are not academia. We don't really focus on academia. We don't really focus on atomic level of this kind of thing, but we also are not industry, even though my company name Sintef Industry, but it's a research organization, and I would say we sit somewhere here. So we take the work that you guys presented, and you will present more hopefully, and we use those model and or theories and try to understand our experiments. Yeah. So what happened? Because the request for the experiment coming from the industry, they have some problem, and they come to us to do some research. And most of the time, research doesn't last for a year or 2 or 3. Sometimes they come and they said, okay, we have this problem. How can we solve? And we suggest to do some experiment if needed, or some modeling work, and then that's how it works. And Sintef is actually not a very small company. We have 2,200 employees and 80 nationalities, so it's very versatile. And among them, 61% is a PhD, and rest are administration and the engineers. Okay, now back to the topic for today. So I work in a formation physics group where we always work underground. It's not not even shallow. We work like more than 500 meters, for example. In most of the cases, it's kilometer, 2 kilometer, 3 kilometer depth. So we think about rock. We think about because rock is always under stress, always. And when we take the rock from the subsurface from 2 kilometer depth, it expands. It develops cracks and stuff like that. So we have an instrument to take this sample back to this stress, and also try to mimic the in situ condition in the lab and do the testing. And we also need to take care of the fluid and the pore pressure and saturation, because when normally we work with the core sample from the field, and when it comes, it can lose the saturation, it can lose some fluid. We have to take care of this. And finally, what we really work with this rock and its in-hold fluid is how it behaves under stress. That's our main objective, how it behaves under stress. Is it, does it elastic, behavior is elastic, or is it plastic? And most of the cases, especially the topic that I'm going to talk today is drilling. This is the place where we really talk about failure. When we don't want to touch the failure mode, but we want to work with in the lab when it fails. So that's our spectrum of work. So for example, this is just an image and the fluid sitting in the pore space and how this combined behavior. So this is the fluid is very important for us to understand how it behaves because it's not only the frame that take the all load, sometimes fluid also carries some load. And depending on the condition of the subsurface, how the fluid will contribute, that we will look into it. So the way we characterize or define the rock behavior is we normally want to see the stiffness modulus of the or strength of the rock. The problem with these attributes is that we measure in a very different ways. Okay, so for example, during when we do the reconnaissance survey, we use seismic. And when we drill, we use also sonic log. So seismic is a very low frequency, like 0 to 100. And when you use the logging in the oil, that is kilohertz in 1000 hertz. But if you do it on the lab, it is megahertz. So the same property, let's say Young's modulus, it's not same. We call it dispersion. We have we try to deal with it. How to there are a lot of work on it about the dispersion and the attenuation of these waves when it moves. And that is one thing we call it dynamic. Yeah, this is called dynamic properties. And we have a static. It's a simple when you take the rock in the lab and you compact and you know the stress, you see the compaction, if it is expand or different situation. And this is what actually, like for example, this is we call it static. And to define the boundary between dynamic and static is the strain amplitude. So if it is when wave move, it also exerts some stress on the sample. And if the corresponding strain is less than micron, for example, then we call it dynamic. And if it is more, like if you compare the rock, it is much more than micro strain. So it's way too much in the lab. But these two dynamic and static is also different. There are many things. It's like upscaling also. You can take it as upscaling stuff. And there are a lot of work. I think still we work, even dynamic to static is still a hot topic. For example, before I go into the main talk of today, I want to tell you that, okay, what happened in the subsurface, we can simulate in the rock. But how we know it's really happening there? We don't have any eyes there. We don't have any camera. We have only option that we can send some signal there, right? We can only send some signal, but it is dynamic. It's not static. So how we will transfer this dynamic to static? Anyway, I'm not going to talk about this. So there are some issues that is still undergoing. There are a lot of theories. As I was discussing with him, that there is a one saying in our world is that all models are wrong. All models are wrong. But some are useful, so that we use these models for usefulness. But still, it's a very hot topic in the oil industry. And again, as I said, the SINTEF kicked us from their poster. The oil and gas is black, but we changed our color. We painted ourselves with a green, and since you paint green with black, it will be blue. So we are a little bit blue now. And we work in the CCS, carbon capture and storage, because if you climate goal is that you have to achieve net zero by 2050, and the first milestone is 2030. So you have to actually really come up with a gigaton carbon storage on the reservoir. And who knows better than us, the reservoir, because we are the experts. So they need us. So now we become getting a little bit greener with time. Uh, so that is also a very important issue here. Okay, oops. And to add into this scenario more complexity, this is one of the things is anisotropy, which is actually the change of properties with angle, right? So especially with shale, sand is it's not really very anisotropic if it is not a layered media, but shale is definitely anisotropic. And heterogeneity is a well-known phenomena for everything when you talk about upscaling. Okay, so how we model or how we see the fluid. So let's say this is a rock, it's a dry rock. So when we compress this dry rock, there is no fluid. So the fluid, no way that fluid can carry some load. And only the frame, the contact, grain contact, the grain contact will carry all the load. So we call it the modulus or stiffness of the grain. This can be also saturated, this can be full of fluid, but if you press it and if you allow the fluid to move out, then no pore pressure development. That means it's also only the frame carrying the load. So we call it K frame, the modulus of frame. And if you saturate the sample and you press the sample in a way that you build up pore pressure. And this is the part where the fluid contribution comes in. And this is famous Gassman equation, and we use it for, especially with sample with enough permeability, or that works best with shale when you have a very low permeability nanodarcy. So the test need to be like slow. So you allow it to move a little bit, and it takes time to pore pressure to move everywhere. But the frame, the shear modulus is same. Because fluid should, at least the water kind of fluid or brine shouldn't have any shear strength. Okay, now I'm slowly creeping into my main topic. So imagine you have subsurface. Everything is nice. Your stress condition is as it is, and you make a hole. So all the stress is disturbed. And if you don't take care well, that how you should you need to think about it, how we can make this hole stable, so that the stress is not disturbing. If you don't, you end up like this. So this same hole is the wall is breaking in, and that can happen is that if you continue doing this, you can end up with like a small pool over there. And you will lose mud. Mud is expensive, and you lose time. So this is the reason why we want this, but in reality it doesn't actually. You never get this, but close to it. And if I don't take care, if I don't understand the stress, if I don't understand how the rock behave, what kind of fluid I should use, what kind of pressure I should put in to drill, then I will end up here. So the borehole will fail, and I wouldn't want it. So to understand this one, normally what we do some testing in the lab. It's a very simple case. So if you do a UCS test, unconfined compressive strength, I would say, and then you end up with a fracture. So in UCS test, this is 0, right? So you just compress the rock, you develop a fracture, and you can use the Mohr-Coulomb criteria to see when rock fails. Normally we use it, and what stress state this rock, the particular rock, needed to to touch the failure. So if you just use this criterion, very simple one, oil industry always try to use the simple method to understand, because I think oil industry has a habit that if they find it that solving the problem need a lot of investment, they keep the problem as it is, so that they're okay with it. They are okay with it because they can survive with it. That's okay. So, but for us as a researcher, we need problem, and we create problem. By questioning, not in the field, but anyway. So this is the shear strength, and in this axis you have the effective stress. So for example, the two the minimum effective, minimum stress, for example, in this case is 0, and the maximum effective stress. This is a simple lab test. And if you, this is effective. So effective means that you subtract the pore pressure from the stress. And then you plot this one, and this beta actually, if you make a center to, if it touches, so it will, this will tell you where exactly at which point it touches the failure line. But if it somehow touch this one, that means you have a probability that sample will fail. That's the thing here. Okay. Now, just a little bit before it was, I was talking and I show you some picture. Now it's in a stress diagram. So imagine you have a subsurface, everything is good. You will drill a well here, but now there's nothing. So the vertical stress, the load of the overburden, and you have a horizontal stress. Horizontal stress and vertical stress can be similar if it is no very quiet area, but if it is like tectonic activity somewhere around, it's extensional. In Norway it's mostly extensional, and in this region I think it's compressional stress. So this can be vary. So in this case it's horizontal stress, and you have a pore pressure. So 3 stress is there. Once you make a hole, then your stress distribution is disturbed, and then you develop a hoop stress here around the hole in the cylindrical coordinate. So you have this horizontal stress become two component. One is hoop stress, and another radial stress is become the flow is similar in the borehole wall. It's similar to the pressure that you put on the borehole. Okay. So now the maximum stress is this, minimum stress is this. So the bigger the gap will be, then you will end up, okay, I think I have this one, yeah. So now this is the typical diagram for the drill oil industry before the drill. So they need to make a program, what mudware they need. They have they collect or they try to come up with the stress measurement from the different layer of the underground, which is extremely difficult. I mean, you don't know the stresses actually. There are expensive tests they run, and so they come up with the stress, and they know the lithology, and they make this kind of figure. So this white part, this is the part that if this is less than, the borehole pressure is less than this line, for example, here, your borehole will collapse. And if the pressure is more than that, then borehole, the fluid will push through, and there will be hydraulic fracturing on the formation. And you want to avoid both. You want to avoid both, and you have to keep your mud wet, that the pressure in the borehole in between this here. So what happens if you have a very low, for example, very low pressure on the borehole? Then, as I showed here, then this difference between the highest pressure in the borehole wall and the lowest will be more, and then you can have a bigger circle, right? Bigger circle, and then you will touch the failure line here. If you move this one here and this one here, that's a problem. Underbalance is a problem. You need to take it very carefully. And if you have you're drilling, everything is okay, and suddenly you encounter a high pressure zone, some pocket gas or something, and then you definitely will touch this area, this zone, because you overpressure, the effective stress will go down, and this curve will move in the left direction, and you will touch the failure line. Your borehole will collapse. There is chance. And also, if you somehow on the borehole, if the pore pressure goes up, okay, then effective stress will go down, and then again the similar situation will occur. So you want to avoid this kind of thing, and you have to study this kind of thing. But if you, let's say, okay, I want to drilling little bit overpressure. This is the most common practice to drilling little bit. You prognose the stress on the formation, and then you keep little bit higher in this window, right? So you have to up this and below this, so that you don't lose mud. Mud is expensive, as I said. Okay. So the talk today, as I mentioned, is osmosis, and this is it's a kind of thing that when it doesn't happen immediately, I will talk detail about it. But before I go to the osmosis, there are other processes that happen with time. For example, consolidation. If you have a pressure difference in the borehole, and the pressure should move across the interface into the formation, and it's a slow process. And I'm talking about today particularly the formation which is very low permeability, and so that the pressure, if it is sand with high porosity and high permeability, you will have an instantaneous consolidation. That's okay. It's a reservoir section, but I'm not talking about the reservoir section. I'm talking about the overburden or underburden. Okay, so where you have a very low permeability, and most of the time, because in sand, when you drill, your drilling fluid have different solids, like a barite, you have a bentonite, many things. When you drill on the sand, what happens? Sand act as a mesh, and then fluid go in, and it leave the solid particle on the wall, and you get a nice cake on the side. It's very nice, stable. It keeps stable. So it's okay to drill in sand. Sometimes if you have a unfavorable condition, the breaking also happen in sand. But the most difficult thing to handle is shale. Most difficult thing. That's what we always worry. And if you want to drill a production drilling, so like you produce something, you change the stress state on the formation on the reservoir, and then you want to drill another hole, these become much narrower. So you are really in trouble. So you need to really think. You need to design the well so that you don't lose this expensive drilling. So, consolidation is mainly, as I said, is in shale, and it takes time. This is important thing, and also mud cooling or heating, depending on the formation temperature and the temperature that you use, because mud always circulate. You have a circulation of mud all the time, because the things that you're cutting on the underground, the chips need to come out. Otherwise, it will be like you will be stuck there. And creep. Creep is nowadays in Norway, or I think in North Sea. It's very I don't know. It's a debate or a blessing or bad. I don't know. But it's creeping is getting attention because in a well you have a casing and you have some space and then you have a formation. And in order to seal the borehole forever, you pray or you have to understand that, okay, if this formation move itself toward the casing, especially shale, because it's a low permeability thing, not sand, and if it does, then you will have a natural barrier. So nothing will move from the reservoir to the top. That is the favorable condition, but sometimes it happens. But during drilling, it's open. It can creep. It can creep so much that your drilling sting and the pipe that you're using for drilling, it will just catch it, and then you're stuck. You try to take it out. If you don't understand or if you don't really close monitor this one, you can lose whole oil. You have to cut it, and they call it fishing. They try to fish, they cut it and then try to fish it, but it's most of the time it's difficult. They have to make a side track. It's expensive, so you need to really understand what's going on, really act fast, really understand the process. So this is the creep, and this is very important or troublesome in shale, especially if you have a kind of expandable clay minerals, like smectite, for example. And the topic today is that chemical interaction. So I will talk about another time-dependent, time-delayed process. It's osmosis, and this is not bad actually. What I wanted to say is it's not a source; it's a mechanism. But it doesn't mean that it's bad. But if you don't know what's happening, if you don't know what kind of fluid to choose, then it can be a disaster. But most of the time, the oil company knows, and I will tell you how they use it. There is a rule, and it's particularly happen when you have a water-based mud. So next slide. Yes. Before, I think before we are become very aware about the environmental issues, we used to deal with water-based, oil-based mud. This is not only that we have oil and we just drill it, because oil-based mud is keep the wall stable. Why? The capillary pressure, because oil cannot, have a high capillary pressure to enter into the shale, right? So most of the time it's more than 10 megapascal, it can be more. And to increase the capillary pressure, they also use some gel. It's like a chemical agent that make a net on the borehole wall, and oil cannot penetrate. But in the same time, this oil-based mud also have a little bit of water in it, emulsion of water in the oil-based mud, and this water can create problem, but it doesn't. But it's very little, because oil itself acts as a membrane, semi-permeable membrane, and the wall itself. I mean, if it is shale, it has also some membrane efficiency capacity. But you cannot use it anymore nowadays. This is advised, or sometimes it is. I'm not sure about the regulation, how it is pushed or advised or suggested. But oil company doesn't want to use the oil-based mud anymore because of the environmental issue. Because you spill a lot of oil on the surface, in North Sea, it's in the ocean. You don't want to do that. You can actually sieve the material, take the oil out, but it's a lot of work. And even if you leave the cuttings on the seafloor, this is oil coated, and you definitely don't want to do that. So they have to use water-based mud. So since they have to use water-based mud, it's better to understand water-based mud, how it works. Okay. So in order to osmosis be a process, the material, the interface, the material that you have in the borehole wall need to be a semi-permeable membrane, right? So if this is not a semi-permeable membrane, it will not work. It will just move like a hydraulic diffusion, pretty simple. But in this case, shale act as a membrane because it has a clay particle which is negatively charged. So that's the reason why shale act as a membrane. What is membrane? I will talk about it a little bit. So just before going into this little bit membrane thing, so I want to say that when you drill a hole, you open up, and things actually happen little bit inside. Not that is actually this model done by Erling Fehr. If probably you know him, Erling Fehr. He's a theoretician, and the creep model he actually gave Sintef a lot money by his creep model. So nothing actually, things happen here, start to happen on the surface, but the failure, according to him, happen just a little bit inside. And things happen here because, as mentioned, is since you open up, this is the place where the largest stress concentration happen, the pressure gradient and the temperature gradient and chemical interaction. Everything happen here, right? Everything. So, so if we look into this area, for example, when the osmosis will happen, if you have a water-based mud, and let's say you used just fresh water, just simple fresh water, there is no ion, but shale has ions. So what will happen is that according to the osmosis, I like the example of like putting salt, making a hole in the potato and putting some salt. After an hour, you see salt gone, it's liquid, yeah, it's osmosis. And so this is same thing. If you have nothing, no ions here, different concentration of ions and different ions. That means no ion, also different concentration of ions and different ions, right? And if it is semi-permeable membrane here, water will move in because this semi-permeable membrane allow water to move in. And if it moves, the consequence I will show on an experiment. And or you in the nature, especially in shale, the salinity is around 3.5. I have seen, I think, 12% salinity in some shale, but it's not very, very common. But 3.5 to 5 is the common, and mostly sodium chloride with some other ions. Mostly sodium chloride in this section, and when you drill water-based mud, normally you put some salt, and I will talk about it with time. Okay, and if you have this situation that you have a different concentration of ion or different ions, then you establish a pressure gradient here. So this is the pressure gradient. So even though you have same pressure on the borehole and the pore pressure in the shale, it is same. Pressure is same, but due to the concentration difference in concentration of ion, then you develop a pressure gradient, and the pressure gradient is depending on the water activity of the drilling fluid and water activity of the shale. So water activity, as I mentioned here, partial vapor pressure of water with salt compared to the pure water. So if you have this difference, despite your pressure is same in both sides, you will have a pressure gradient. You will create a pressure gradient. And this disturbance, you see here, it will propagate with time slowly, and that will be actually dictated by the pore pressure diffusion constant. Okay, so this is pure fluid. The water is only moving in. I'm not talking about anything, just water moving in from the drilling fluid to the shale. In the same time, since we know from many experiments, we know that shale is not a perfect membrane. If it would be perfect, that would be like membrane efficiency. There is a parameter, it is in the next slide. Membrane efficiency should be 1. That means it's only allow water, nothing else. But shale is not. It's a leaky semi-permeable membrane. So ion, not only water is moving first, but also a little bit of ion will start to move in. Okay, and what will happen? This ion movement also we call it ionic diffusion constant, is actually the constant number, and then that will dictate the movement, and depending on the concentration and the types of ion. Okay, so if that happen, the gradient that you created just exposing two different ionic concentrated fluid, it will diminish, right? So with time, the pressure gradient will go away. But this process is a time consuming, time dependent. So to incorporate this membrane efficiency, we can incorporate this membrane efficiency here, and this is the standard equation for osmosis. So it's begin with the pressure gradient, and yeah, so we can measure in the talk here today, where I will show some experiment. The main idea was to actually calculate this one. And okay, yeah. So the parameter, I will show you experiment. So before going into the experiment, I wanted to measure how good the membrane efficiency of this shale that I'm measuring it is, and the hydraulic diffusivity, and the ionic diffusivity, and also chemical strain. So before I go into the test, I would like to talk about a little bit about chemical strain. So now you understand why the pressure move, why the fluid moving, so ions going in. But when since you have a clay minerals, and I'm talking about abundant amount of smectite on your clay, then what happen if you have some sort of ion, mainly potassium, it moves into the shale and it kick the sodium ion from the shale, and the lattice becomes smaller and sample shrink, and so that is chemical strain. Okay, and if you just have a water, no ion, fluid will go in, and the lattice in the smectite, it will expand. Yeah? So this is chemical strain, which is very important. This is a one test. I have made a couple of tests. I think 4 tests after a lot of failed tests. So what I did, there are big story behind this point. I'm not going to go into this. So I I put a sample and the fluid on the top under pressure. That is in situ condition. The pressure is like this is hydrostatic pressure from all the side. This is about, I think, what is the pressure here? This one, yeah, 14 megapascal, 140 bar, and the pore pressure, the sample and the fluid on the top is exactly same pressure. The difference is the ionic concentration. The sample has 3.5% sodium chloride. The exposed fluid that I measured with is like sodium chloride, 8.8%, and calcium chloride, potassium chloride. And the difference in concentration, but the activity is same. So I keep the activity because the osmotic pressure depending on the activity, not the concentration. Okay. And what happened when I expose it? Immediately, the pressure went down. No, it's not an assumption. Activity, actually we have equation, empirical equation. Yeah, it's not a purely assumption. You can actually measure it. Yeah, but like for example, if you have a 3.5, I mean you can measure it at the relative humidity, right? On the desiccator, and you can put different salt, and there are paper by it, and we just, as I said, I'm the intermediate user of the models. I used models. Can I? Yeah, changing the salt. Yeah. And immediately, not immediately, the pressure start to drop because it's sucking the water from the shell. And then when the water fluid reaches the end of the sample, and then this hydraulic diffusivity goes down or off, and the ionic diffusivity start, and eventually it come back to the equilibrium again. And in this test, I just expose the sample with fresh water to see can I get back the compaction. Like this is the compaction, how much sample compact, yeah. And I ended up with like, okay, I lost, the pressure went down to 2.3, but when I exposed it to water, it also gained 2.3. So with this test is with sodium chloride. It's not it's understandable that sodium replacing sodium is not really a big issue. It was there. The pressure went down, but when I exposed to the water, it came back. But that is not the case with KCl, because the KCl ion is smaller. When it go in to the lattice, it shrink. It doesn't really want to come back to the expansion again. Okay, so what happened? Here, this is borehole. And this figure is made by Arling, and he asked me to if I want to use it, so I used it. It's easy to visualize. So this is your borehole, and you have a concentration of ion is 20% here, and the shale is 3.5 or 4, and this is pore pressure. In the beginning, you have it's a drop here because the oil pressure. In this case, its oil pressure is a little bit below. What happened when you expose it with time? This is the time axis here. Pressure goes down, and this down pressure, this settle here, it's move in this direction. Okay, and then finally it equilibrate. So that slice is time slice, and this is after the test. But you see, that slice was like I made a slice here, 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 here. In this test, he made the slice. He measured the pressure in different place. I mean, like changing z or length parameter. But here is the real test. Sorry, where we have the sample, 10 millimeter sample, fluid exposed side, the same pressure, and pressure measured in the bottom. So you see, this is the part where you have developed the osmotic pressure. This part is not only, as I said, it's a leaky membrane. It not only hydraulic diffusion, it's also ionic diffusion, right? And the next slide, you have ionic diffusion. So from this picture, we can calculate the hydraulic diffusion and the ionic diffusion and the membrane efficiency. Okay, how much time I have? Okay, now I will briefly talk about this is the pressure part I talked about. Now the shrinkage or expansion part, okay. So I expose the sample three different salt with same activity. So what happened is that, as I already told, that okay, when these two different concentration fluid come together, ionic exchange start to happen, okay. And depending on the ion on the both side, the sample, the borehole wall, or that can shrink or expand. And so when you shrink the wall, and it gets a little bit bigger, right? When you shrink, what happened? You remember the tangential hoop stress? It comes down. I will graphically show you later after this one. So it is actually similar to the cooling or heating the borehole. So this is how it happened. When you shrink the surrounding rock, this is the tangential stress, and this is the concentration again, the same. And if you, with time, the hoop stress goes down, and it settles in a number, and then it start to move toward away from the borehole wall. Yeah. Okay. So now, if you look at the test result, you have a sodium chloride. This is the zero line. Sodium chloride, calcium chloride, and potassium chloride. Sodium chloride is expected. It will not actually exchange a lot of things. So the compaction is very little, and surprisingly, calcium chloride also have a compaction. But theory says that it shouldn't, because the calcium ion is bigger. When it moves in, it should actually expand a little bit. But experiment didn't confirm that. But KCl, which is most important, that confirmed that the compaction is much higher when you have a KCl, because KCl have a high, it's small, and the lattice space in a smectite, which have a double layer of water, which we call bound water, along with free water in the middle. It likes K, the potassium ion. It move in, kick the sodium out, and shrink. And that's why the shrinkage is higher for KCl. So what happened with KCl is, if you shrink, your hoop stress goes down, right? The minimum stress is there, the radial stress that if you remember, but the maximum stress goes down, and then circle becomes smaller, your borehole is safe, okay? And in the same time, your pore pressure actually going down, and when your pore pressure goes down, effective stress goes up, and you move the circle in this direction, and it's also getting away from the failure line. So using KCl shrinkage and dropping the pressure is very favorable. Okay, I'm close to the end. So here is the conclusion that I come up with. So despite you don't have any pressure gradient between the interface in the borehole wall, if you have a concentration gradient, you will have a flow. So that's osmosis, and fluid flow can change the pore pressure in shale, and depending on which direction is changing, you either have a stable borehole or an unstable borehole. And decrease in pore pressure due to the osmosis with a high concentration of saline on the borehole, it actually helps to stable the borehole wall. And shrinkage also help if you use KCl. And the reason why it helps, because it's decrease the hoop stress. So now in a practical field, this is only laboratory-based experience, as you said. We don't know what happened underground. We really don't know. So how to measure this one? That's the challenge, still challenge. Oil company use whatever we say, or whatever they come up with, they use. And if it works, it works. If it doesn't work, then go to the next solution. Okay. But how you will measure this one? I mean, in borehole you can measure like you send a log tool. I mean, again, it's dynamic to static problem. But let's say you send a log tool, but you cannot do that because you are actively drilling now, and taking out and setting the thing is out of question. It's a lot of time. So still, I think they're struggling to really monitor, to really validate the thing. But it works. And what they do they used 12% KCl. I think, I don't know the number, but I think most of them are almost even close to 100% drilling. They use 12% KCl when they drill with water-based mud. And of course, they also add some additives to help it. But there is no proof. There is no proof that it works. But it's all except the laboratory experiment. But it works. That can be really backfire. They know it. It really can backfire because you may have some natural fracture on the wall. And what happens if you have a natural fracture and you squeeze part and then it will be loose? So, yeah. So they don't. It's not advised to use when you have a natural fracture in this on this shale section. Yeah. I think I'm done.
That's out. Questions?
Thank you very much for a very interesting talk. It's all about application, and it is really very thrilling. Especially so for me, as I come from Kolkata, east of India, where under the river Ganges, we have a metro. This is just a comment, nothing to do with your talk. They have drilled, there are twin cities of, one side is Kolkata and the other side is Howrah, two big cities.
Yeah.
And they have the Ganges, which is very broad, quite broad there. Yeah. And they have the metro, the railways have bored a drilled a channel, which is 15 feet below the river bed, 15 meters rather, sorry, or kilometers, meters. And it is and it's clay soil. Yeah. This Ganges is absolutely clay soil. It was a big engineering channel, and it remains quite a marvel. And I mean, I do appreciate the trouble of drilling and keeping the mud not falling into the drill, and to then sort of hold it there, and ultimately to lay cables and build a rail station. I was just thinking it must have been a great engineering feat and a lot of science behind it.
Indeed, I mean, like it's there. I think, I don't know. I mean, I've been to Kolkata once, but they are not only dealing with this kind of problem. They also deal with I don't know how deep the water reservoir is, the aquifer is.
The height of water, like, it's the on top. I'm saying 15 feet below the riverbed, and then the Ganges is deep enough to have barges. Yeah. So it's a very deep. The river is very deep there. Yeah. So much weight of water, and then the very, very watery clay soil, and to do it, I mean.
That's really. I mean, I think Alex.
They brought in engineers from Norway and from Germany.
I think that's my comment was like Norway has a lot of underwater tunnels.
Just to share that information, we were like absolutely very, very happy with that.
I mean, I think this is they've made a right choice to take the engineers from Norway. And wherever you go, it's a fjord country, and it's a lot of underwater tunnels, roads. This is really marvel engineering. I mean, like this one, for example, this compaction or things in Norway, there is a field called, I think, Ekofisk. Yeah, so this compaction happen. They have a chalk carbonate reservoir, and they think, okay, the pressure is going down. We will push some water in the chalk, and the chalk was soluble to water, not fully, but little bit, and that create the more compaction. And this compaction under 1.5 kilometer, the whole surface sunk 10 millimeter. How important it is to understand the things. Yeah.
Any other questions or comments? No? Thanks, Mohammed, again. It's a really nice talk. And then we can continue. It's the last talk of the day. Suman Dutta. instrument data is coming from ICTS in Bangalore. And we talk about yielding by impulse stress. Okay.
Thanks. Thanks to the organizers for giving this opportunity to present my work here. It's always great to be back at IMSC because this particular work that I'm going to talk about today was initiated when I was here. And the work is in collaboration with Pinaki Chaudhary, who is here, a faculty, and Christian Martens from LIFI, University of Grenoble Alps. And this is a work which we started from 2018, and I am now at ICTS and NCBS. And I think the conference dinner is not far away, so everybody is feeling a bit hungry and they are also tired. So it's my responsibility to start things with some foods, which is the main topic today. So this one, the advertisement that you can see has been a golden advertisement in 90s. We were the 90s kid and we used to see this kind of advertisement. So this is a ketchup. As you can see, it's coming very slowly. And this is a mayonnaise, which is once we press it, it comes out. So these are the typical examples of an ill-stressed material, and these are the ill-stressed food that we see every day in our daily life. So the typical behavior and the physics of this food is this. So you have, initially they are in kind of a solid-like state, which are the viscoelastic solids, and then they, as the shear stress is increased on this material, they suddenly fluidize, and suddenly there is a drop in the viscosity, and they become fluidized, and they become viscoelastic fluids. So the question is, do we understand this regime, where there is a sharp drop in the viscosity, and how to understand this behavior of yielding? So this is the yielding transition, and the kind of material that you can see, these are all amorphous in nature. So we want to address this yielding transition. I think many of our earlier speakers have talked about this, but this is, we are going to address the same question using molecular simulations. And as these amorphous materials, they vary in size, they appear in different forms, shapes, and things can be athermal, things can be thermal as well, depending on their size and shape. And these are the typical behavior that this class of materials show. So this is the typical load curve, this is the flow curve. So what happens, for example, if we go back to the earlier picture, initially when we are just driving it with some stress, when it is being deformed linearly, the first initially it behaves like a Hookean solid. So this is the initial part, and then after some plastic events, they either fails, but that happens in case of a brittle failure. But these are ill-stressed materials, so they becomes constant here, and they show a steady flow here, and that separates it from the other kind of materials. Okay. So for ill-stressed material, one of the criteria is that the steady stress that one has is a constant. Okay. And we, as I already made clear the question, what we are trying to understand is this unjamming transition. And this is the very famous Liu and Nagel phase diagram of jamming. So where it shows that this is the 3-dimensional phase diagram. So, this is on this axis we have the temperature, here we have the load, and this is 1 upon density. And the kind of question that we are going to address are valid for t is equal to 0. So, because we are dealing with the materials, they are not responsive to the temperature. So, these are all athermal materials. So, we are at t is equal to 0. So, that is basically the blue plane. And then what we are trying to address is that we are going to see what happens, for example, when the material becomes liquid from a glass state by some loading. So, that is the question, and this is what usually happens, and one can see these beautiful microstructural changes in the experiments. So, this is some colloidal gel at rest, and when it fluidizes, this beautiful network structure gets disappeared, and you see that it becomes a part of a fluid. So, and every real body yields. So, this gentleman already realized almost more than 100 years back, and we are trying to understand exactly this thing for those kind of materials for glassy systems. So, these glassy systems means things are slow, very, very slow, and what happens, this glassy material can also have a different kind of characteristics depending on their preparation. And so, in the experiments, what people have already realized that different kind of glass has got their different response, and for these class of glassy systems, glassy yield stress materials, that what people have seen and which is also valid for the other class of yield stress materials is that things flow beyond a particular stress threshold. So, in the creep curves, one can have these 3 different regimes. There is the primary regime, then you have the secondary regime, and there is a third regime when it flows. Otherwise, it is getting absorbed at very long times. So, this is from some experiments, and people have also tallied the experiments and simulations, but mostly the microstructural changes when things yield are not well investigated for the athermal materials. So, this athermal creep has been quite open to understand. So, we studied this using some framework, molecular dynamic simulations. So, these are the first principle approach to this kind to address this kind of problems, and the framework was developed by in this work, where we can see that the athermal creep and this kind of an power law creep has been seen for the Yukawa glass, and this is the framework. So, in simple thing, the sigma naught is the imposed stress, and how with this imposed stress, the material response that generates the gamma dot or the shear rate. So, this is how things are changing, and this is our framework for creep. So, with this sorry, yes. So, that is for the mostly for the brittle kind of solids, but for example, the examples that I showed in the beginning,
right.
For example, you have this mayonnaise.
No, but in glass I am talking about.
It's not, these are all glassy materials, because for example, their structural time scale is very, very long. It need not to be the window glass.
Thank you.
Because the kind of materials that I am showing here, all these amorphous materials, they are mostly all are in the glassy state. So, their structural time scale is very, very long. And I will also show, for example, when things change and change its rigidity, and how this response, for example, in one of the case it fails like a brittle material when you have the beautiful slip line, and other case it shows a flow. I will separate all these cases. For example, this is exactly this question we try to understand. For example, we have these glassy materials of different levels, and people have seen that for different levels of glass has got different materialistic properties, and in the earlier works people have seen, for example, if someone is having low energy glasses, they behaves like a brittle glass, brittle materials, while the high line states, they behave like a ductile material. So the response is different, and this is also because just because we know how to prepare different levels of glass, we can also play with their materialistic property and the material and the dynamical response. So exactly the similar kind of thing we try to address, whether that is achievable in creep or not, and whether do we understand this change, the dynamical response under creep under this kind of framework or not. So we take these different levels of glasses. We have this HTL, ESL and the GQ. HTL is a high temperature liquid, the glass prepared from the high temperature liquid states. ESL is the equilibrated supercooled liquid, the glass corresponding to the equilibrated supercooled liquid, and GQ is a gradually quenched sample. So this is a very low line state, and this is a midline state, and this is the high line states, and we are looking at the creep response of these different glasses. And what happens that the static thresholds, we found that they are very different, even though their dynamic yield threshold is identical. So what is happening, for example, for HTL, this yield stress is close to 0.4, while for the ESL it's something between 0.53 to 0.55. So here if one imposes some stress, if the imposed stress is larger than this threshold stress, it flows, otherwise it gets absorbed. For the GQ, this number is quite high, just because this corresponds to the very low line states, and this is subject to some rejuvenation by which it gets activated and gets out of this minima and becomes liquid, and it can only be liquid, for example, when it crosses this regime. So if they cross this part, they will become free, and that will the fluidization process. So that's the energy hypersurface, and we try to understand the same thing from microscopic point of view. So this is what happens. For example, if we have this kind of a material, and this is what this GQ sample we test with, and we are putting some stress in two different cases. In one of the case it's flow, another case it's non-flowing, and the amount of stress and its difference is infinitesimal. So in terms of the value, in one of the case it's the applied stress is 0.79, another case it's 0.795. So the stress difference for these two cases are of the order of 10 minus 3. So it's a very small amount of stress, but that is leading to a very different outcome. In one of the case the material flows, another case it doesn't. So what we are showing here are the local fluidizations. So if a zone has fluidized, it will turn from blue to red, from red to blue, or if it remains in the stuck, it will be red. So what we can see, for in the non-flowing case, there is a percolating backbone. Up to this point, in most things are identical, and then for this non-flowing case, you see this backbone, but here that backbone gets dilated and the system achieves a flow. And this is the distribution of this local overlaps. That also gives us some more insights about this thing, because when it's not flowing, the distribution is a delta function at 1, because 1 is for when it's stuck and 0 is for when it's flowing. So this is like a local order parameter for this associated transition. So it's a delta function in the beginning, and we are evolving it with time, and when it has flown, the system has achieved flow, we see that this part has gone down suddenly due to this rapid avalanche, and then things are close to 0. So this is what happens in the vicinity of the yield threshold. So we are sure that system is behaving like a critical solid here, and the system is showing some kind of so this is another way to look at this, and this is a larger system we deal with, and here we see for example, so this is the same sample, this is a larger sample, and what we are showing are the local mean square displacements and the local vorticities. We are showing and how, so for example, when the system is exploring this kind of a transition, and we are comparing the flowing and the non-flowing case. So these are the local MSDs for NF non-flowing case, this is the flowing case, and up to till this point C, nothing, the microstructural changes are almost non-significant, and then at this point you see this beautiful slip line, but that only appears for the GQ case, and then in the long term this part gets it gets fluidized, it doesn't, and this slip line forms due to the accumulation of these plastic events, rather the vorticities. So you have these vorticities and its accumulation that actually creates the slip line, and this slip line not only appears at the microscopic scale, but it also shows some scale free nature. So if we just change the coarse graining scale, we can see the slip line at different coarse graining scales. Yes.
Is like curl of flow velocity. I mean, is defined that way in fluid dynamics. Are you meaning vorticity in the same sense?
Yes, exactly. So this is basically the, for example, when you have the velocity information, you can take the curl of it, and you have to take the local, you have to compute
contour.
it locally.
But then why should it form a vortex? Is there any reason why it should form a vortex?
Well, for example, from microscopic point of view, for example, these are collisions. For example, when the material is getting stressed, so it will induce the local collisions, because after all it's the mobilization that will make the system flow. So that will, so for example, when this local collisions will happen, and that will somehow have some randomized effect, and that will lead to some local changes. These are completely stochastic in nature. These are the plastic events, and these plastic events, and only it's, for example, when they self-organize, only when and that length scale of that change spans the whole system size, then only you see
I understand, but my point was that these clusters, these little dislocations, if I wish to call them, will come and align themselves, and then I mean, to call it a vorticity, which has a different, I mean, are we very sure? That's what
vorticity is just by definition. Okay. This is basically system spanning length scale that you see. Vorticity is by definition, and well, yeah. Okay, so and yeah. So the response at all scales matter. So we see this slip line that is happening at all scales, and things are critical just because the system is responding at all scales. And this is also seen in at a macro scale. For example, if one does the experiment with different samples nearby the threshold, some of the samples show failure, some of the materials doesn't show failure in the vicinity of the yield threshold. So this is what this bifurcation can be seen at the macro scale. In the micro scale, what happens if one tries to understand the local persistence, and these are the local time fluidization time scales if one tries to compute. So then, so this is a time scale associated to some local fluidization. So that is defined over the local mobilization. So if some region has got some displacement which is larger than some threshold, we call this region has fluidized. So then it will turn to white, and at what time, that will give us the fluidization time scale. So when we have this black region, these are basically non-flowing regimes, because these are having a very high fluidization time scale, which is much more than the observational time scale. So, and this backbone appears at all scales. So 1, 2, 3, 4 are corresponding length scale associated to this coarse graining scale, and this is for the case when it doesn't flow, and when it flows, that we don't see that regium, that backbone. So for if we see if we try to compute this susceptibility out of all this spatiotemporal heterogeneity, for the non-flowing case we see that this backbone and the associated fluctuation remains for a very long time, while for the fluidization all the region and the response becomes 0 at long time. So, means that that ensures that the system has fluidized at all scales. So, now we are trying to address another question, that if the system is critical at this point, so what is the nature of these fluctuations? What is the nature of these critical fluctuations? So, when the materials yield, we try to figure out what we are looking at. We are looking at the fluctuations of the velocities, because the velocities are the displacements and displacements are non-affine here. We are looking at the non-affine displacements and its fluctuations, and those are non-Gaussian in nature. So, what we are doing here, as with the time we are probing the velocity distributions, the non-affine velocity distributions with time and their associated behavior of its moments, and we recently have figured out a good measure of non-Gaussianity, which is based on the information theory, and this measure we have shown that this is much more efficient than the conventional measure of non-Gaussianity, and that was originally proposed by Solomon Evan, Sanjay Kumar and R. Simon. So, and this relative entropy measure, relative entropy based measure, that actually computes the non-Gaussianity of these distributions and its evolution with time. So, what happens at every point we are computing the distributions, and the construction is very simple. At every point of time we have got some distributions, we have to find out its nearest Gaussian. So, in the nearest Gaussian consist of it's a Gaussian with the same first and second moment identical to the given distribution, given non-Gaussian distribution. So, this is how we compute for example, if we see that this distribution, this red line is the nearest Gaussian, and the statistical distance between these two distributions will give us this non-Gaussian parameter. And this is the behavior of this non-Gaussian parameter as a function of time for 3 different states. So, what happens for this GQ case, in this case we are imposing the same stress value to all 3 different levels of glass, and in the end they becomes identical, and as all these different glass loses its memory and they becomes identical, but their transients are very different. Here for the GQ case we see that these 2 prominent time scales are there when this non-Gaussianity becomes significantly high. So, there is a first time scale around this point which is not very significant. So, there exists one first peak, and the second peak appears somewhat here close to this point, and for the ESL we see that these 2 peaks are there, but the difference between them are less. For HTL these 2 peaks have merged and becomes 1. Okay. And for example, if we want to probe this behavior for a single state, but for different values of stress, what we see here, the second time scale becomes very responsive to the imposed stress, and the velocity inhomogeneity is very different for different values of the imposed stress. And the question then becomes, what is the typical behavior of this, and can we make out some predictions based on this behavior. So, the key observation of this investigations was that we figured out that the 2 time scales exist. The second time scale is important, and this is responsive to the imposed stress, and the third point was this steady state velocity inhomogeneity, and that is dependent on the stress, and this is what we get. So, this is the imposed stress value and this is the steady state non-Gaussianity, and that shows very surprising behavior. So, so now this is behaving like, so this is this log of delta S and G that linearly depends on this 1 by sigma. And recently we also did the similar kind of investigation for a passive fluid, and there also we saw the similar kind of behavior is there. So, and which is very surprising that even the behavior of this liquid state inhomogeneity is very similar for the passive fluid as well as the driven as well as the driven fluid. So, this is seems like this negentropy or this quantity is showing some kind of an universal behavior. Question we are investigating now, can we see the similar kind of thing in case of some active fluid as well? We will have answers of that within very soon. And however, for this this transition and then the final thing that we have, that what leads to this kind of a fluidization. To address this, we have got this information theoretic framework, and based on that we compute the change in the informational entropy for example when a system flows, and in another case when it does not flow. So, what we are comparing here, so this F stands for the flowing, NF stands for the non-flowing, and this Vx are the velocity distribution. So, we are comparing the distance between the instantaneous flowing the velocity distribution in the flowing state and the non-flowing state, and that will give us the entropy production. And that also shows that this will have a discontinuous jump at the static yield stress. So, this is what the nature of the transition is. So, and this analysis is based on some of this non-Gaussianity, because that is a spontaneous question that one can ask, that how to realize this non-Gaussian regimes. So, and this entire transition can be, because that is the dislocations that happens. So, to understand those rare events, because I said these plastic events are very stochastic in nature, but question and also what I said, that their spatial accumulation finally leads to the failure. That could be understood using this investigation, where we are showing that these extreme velocities or the extreme displacements which are beyond 2 sigma and 3 sigma are responsible for this kind of a failure, and this failure leads to this this drastic change, and this is the disorder in the system that is making the system liquid. So, in summary, that we have seen the yield stress materials, and we will explore them very soon, and they yield beyond a particular threshold, and then we showed that different levels of yield stress materials show different kind of response, and their material origin controls their creep response, and this creep response and the associate and the yielding by this creep is driven by the last spatiotemporal changes and the fluctuations, and the system lies in the critical state near the yield threshold. When it flows, there is a dilation of the backbone, and when it does not flow, remains in the absorbing state, and the critical fluctuations associated to yielding are non-Gaussian in nature, and the non-Gaussianity measure that we deal with the negentropy, that shows some kind of an indication of an universal behavior nearby the threshold, and the informational entropy approach that we have shown, that shows a discontinuous jump across the yield threshold. So, this is the work that was ongoing, and we are communicating this work, and out of this microscopic information, a simple questions come: what emerging macroscopic picture do we have, and how we understand them. So, for this we tested some elastoplastic based model. This is a lattice based model, which is very this has got some very similarity with this earthquake model by Bakhchen Abukov. And what happens, so we have this lattice, and every point we have some variables like the stresses, and this stress and its change, associated change, depends on these three different things. One is the elastic deformation, and then we assume that the plastic events are happening, and then how these plastic events are correlated, and we use this kind of a propagator to correlate these events, and then there is a stress redistribution that is happening due to the plastic events. And this is what the form of the model for the imposed stress and the imposed strain rate. And here that you can see, this Gij is the propagator of this kind of a form, and we have this tau plastic kind of a variable which depends on this Nj, and this sigma j are the local stresses. This Nj depends on these two other parameters, this tau plastic and tau res. Tau plastic is the time over which a local region remains in the plastic state, and then this tau res is the time scale over which it actually remains in this residual state. And this we do for each of the grids, and this makes our model. And to make its model and how we predict it, we have this model and we feed some microscopic information from our microscopic simulations, and we do this elastoplastic model to make some predictions. So, the key ingredients for this are the stress field and the local yield stress field and the flow curve, which we obtain from the microscopic simulations. We feed all these things into the elastoplastic model using the and then we make some predictions about the onset of flow for different levels of glass, and we compare it with the microscopic simulation to verify whether the predictions are robust or not, and whether this prediction holds for all different classes of glass or not. So, this is what we obtain, that for different values of the imposed strain rate and the imposed stress, the elastoplastic predictions are quite robust. It also holds for different levels of glasses. This E1, E2, E3 are the different levels of glass. So the framework that we have had are quite robust in predicting for different large class of the amorphous solids, and in predicting its yielding behavior. So that's that was published in PRL a couple of years back, and this is another exciting story of yielding, that's by activity, that is also ongoing work. I just wanted to advertise this work. So you can see here these failure modes are different. It's not the failure line. Here we have the cavities that is appearing, and this formation in the cavity, and they are quite turbulent in nature, and we are trying to address the similar kind of questions, and some of we have already got some of the answers, and we see that the liquid state of this kind of a model are actually again critical. And another funny thing is that when we have such kind of liquid state by some fluidization upon activity, it also jams, and the jamming preceded by some plastic events, but the overall things are not reversible, and the jamming is another fascinating story, and it shows different, for example, again it also shows the existence of two different time scales, where one of the case this is upon reduced activity. So one of the time scale is here, another time scale is here before it finally reaches the minima. So it's like how things think from a liquid state and how it goes back to the rigid state again. So these are the exciting stories, and to make a conclusion out of all this work, so we have seen that the elastoplastic predictions are quite robust in predicting the failure or the yielding in large class of amorphous solids. Yield stress materials show critical behavior near the yield threshold, and the critical fluctuations are non-Gaussian in nature. These are the conclusions of our work, and I'd like to thank you for the patience, and I think I'm done.
So questions?
Regarding the non-Gaussian nature of the fluctuations, you use this concept that it's not familiar to me of negentropy.
Okay.
Can you give some physical insight on the meaning of negentropy, please?
Yes. For example, the first example that we dealt with was the process of the diffusion. For example, if we take the simple liquid, if we take the diffusion equation, the solution is a Gaussian. Now, for example, when we have the diffusion equation, the solution is a Gaussian. Now, for a heterogeneous or a complex fluids, we can think of that there are some additional terms over here. So, that will make non-Gaussian, right. So, now in one of the case it is fully diffusive, another case it is not, it is complex. Now, the way we have defined this negentropy is based on that picture, because when we have this PNG or the for example, if we are given some non-Gaussian distribution PNG, every time we are constructing its nearest Gaussian. So, for example, when we treat this complex fluid example, it's actually taking care of its nearest diffusion and trying to understand, because the Gaussian are always having the maximum entropy. So, that will make it a positive definite quantity. So, this is what this the definition is actually taking care of a distance from its maximally disordered state every time. So for that the complex fluid example, so whenever we have this additional term, if we operate this measure with time, what it will show, for example, we have this we have the data, I can show you the exact thing. No, I think I don't have the data here, but the thing is, for example, when we have the supercooled liquid, that's the identical example of this thing. So we are actually shifting from. So this is the diffusion equation, and for example, if we have some additional term, so it will become non-Gaussian, and if we have got some intermittency in the model, that gives us the sense of this heterogeneity. So then it will have a behavior like this. So non-Gaussianity as a function of t, and that will be the time scale associated with the heterogeneity, right? And that the quantity, the way we have defined. So this is, for example, if we have this distributions, any distribution PNG of x, we have to first construct this nearest Gaussian of this thing using the first and second moment of this quantity every time. So this is the constructions, and the quantity that will deal that will extract the information associated with this heterogeneity. Is that clear, or maybe we can discuss more?
I have a related question.
Yes.
This is that even if they are non-Gaussian, your distributions remain symmetrical around zero. This is because there is those symmetries are intrinsic to the system. The fact that
this is shifted. This is shifted. For example, if there's any drive, but because the constructions, for example, you can see, even though they are not symmetric, for example, it can happen that this is skewed in one side, but no.
Doesn't
okay.
seem to be.
No, I think you are asking about this, right?
Yeah, exactly.
Okay. So this is symmetric means, for example, the center of mass remains in the same thing.
Exactly. Okay. So there is
that is one confirmation of the simulations are correct.
Thank you very much.
But what we are dealing with this thing, this can be skewed. So the measure is taking care of this skewness and how skewed they are, that we can understand using this.
Okay. Thank you.
Yeah.
Yeah. Hey, thanks for a nice talk. I missed something. So you were showing like HTL, ES, and
Yes.
then so what are
Shall I go
those
back?
actually? Yeah.
Yeah. This one, right?
Yeah, yeah. So what are these by the
Yeah,
way?
I'll explain it. Okay. So for example, if we have, if we just think of the hypothetical picture, landscape picture of the glassy material, we can have the liquid-like state. For example, if we start with some liquid-like state, and then what happens as we are just trying to figure out the nearest minima to the liquid state, those are usually the glassy states, provided we bypass crystallization, right. So we start from here, for example, this is the liquid state, and then we are trying to find the nearest minima. And now this HTL state means this is how it is prepared. We take the liquid state and we try to find its nearest minima. That's a high temperature liquid, and we just quench it. So this is how we can have this kind of state, because it will lead to the nearest minima to that liquid state. And now if we sufficiently cool that liquid and we can equilibrate till nearby the mode coupling temperature. So this ESL is a low temperature state, and from there we are finding the nearest minima. So then we are stuck in this basins somewhat. So these are secondary levels, and then if we just do some slowly cooling protocols, then what will happen, it is going to explore and the lower and lower levels, and then if we just try to figure out find out the nearest minima associated to this very low temperature states, then we can prepare this GQ-like of states. So these are glass samples associated to these different levels of liquids.
Fine.
Is that good?
Yeah, sure, thanks. And the other question was, you said like, there's a backbone in one of the case, and that
Yes.
backbone is, what is that backbone? What is that quantity essentially?
What is the understanding of this backbone?
Yeah, yeah. So what is that quantity? Like, when you show that backbone, so what is
so
that
this
quantity?
this is the fluidation time scale which we have defined over it. The same backbone we can see from this.
So what are those plots, by the way? Like, yeah. So what are, this is the field of view, right? So your simulation domain.
Yes.
And then what does that white color denote?
Okay,
and what is the
these
black
are
color?
the local fluidation times.
Local fluidization
times.
or
At
the
what point
relaxation
of
times
time?
locally.
So we define some thresholds of some displacements locally, and if it crosses that local threshold, we make it white and we make it black, depending on their
So
time
black
scale.
ones denote they don't fluidize so easily.
Yes, exactly what it is. So they fluidize at very large scale comparing to the experimental scale.
Okay.
It is much larger than the experimental
Yeah, so
scale.
they are forming a backbone, you're saying.
Exactly.
Okay,
Yes.
thanks.
Any other question? Comments? Okay, let's send it again. And thank all the speakers of the session and all the day. I don't know if there is some comments by the organizers. Okay, great. So